Hello everyone, this is Ashwini. Today I am here to give a project review on a novel DC to DC converter battery modeling for reducing emissions from hybrid electric vehicle using nonlinear techniques under the guidance of Dr. K. Dhananjay Babu. Outline of the presentation, objective, introduction, existing method, limitations, proposed method, working, simulation results, advantages, applications, and then conclusion. Objective. The main aim of the project is the design a novel DC to DC converter battery modeling for reducing emissions from hybrid electric vehicle using nonlinear techniques at different voltages. Coming to the introduction, hybrid electric vehicles have emerged as a promising solution to address the challenges of environmental pollution and energy sustainability in the transportation sector. By combining an internal combustion engine with electric propulsion technology, hybrid electric vehicles offer reduced emissions and improved fuel efficiency compared to conventional vehicles. Central to the performance of hybrid electric vehicles is the electric traction system, which controls the flow of energy from the battery to the wheels. Optimizing the efficiency of the system is crucial for maximizing the benefits of hybrid technology. This project presents a novel approach to electric traction system in a hybrid electric vehicles aimed at enhancing efficiency and reducing emissions. The proposed scheme integrates several key components, including a DC voltage source supplied by a battery, a DC to DC boost converter based on MOSFET technology, a DC to DC buck converter controlled by pulse width modulation technique, and two electric permanent magnet motors controlled by Lipno techniques. Coming to the existing method, a linear DC to DC converter uses a resistive voltage drop create and regulate a given output voltage. Linear regulators, which are used to output a stable DC independent of input voltage and output load from a higher but less stable input by dissipating excess volt amperes as heat, could be described literally as DC to DC converters, but this is not usual usage. DC to DC converters are devices that temporarily store electrical energy for the purpose of converting direct current from one voltage level to another. Limitations of the existing method: less efficient of power, larger in size, more heat produced, output voltages are less than input voltages. Coming to the proposal method, electric vehicles are a solution for the environmental problems caused by vehicles with internal combustion engines. The advantages of EVs include energy efficiency, virtually lack of pollution, and the availability of electric energy through electric distribution systems. The other major factors include optimum design of the motor, selection of proper drive, and optimal control strategy. DC to DC converters are used to convert unregulated DC voltage to regulated or variable DC voltage at the output. The DC to DC converter plays an important role in regulating the power flow in various systems, especially robots and electric vehicles. The battery bank voltage will vary with the operating conditions of the vehicle. Proposed method diagram. This is the proposed method diagram. In this project, there are different types of batteries we are used. In this project, we use lithium ion battery. This is the battery, and this is the boost converter modeling. This is the buck converter modeling, and this is the motor characteristics. In this project, we use scope. Scope. This is the scope because throughout time period output will be analyzed. In this book boost converter modeling, capacitor, series RLC branch, that means inductor, switch, diode, and another capacitor. The main purpose of the capacitor is acting as a filter to the battery. When the switch is on, energy will be stored. When the switch is open, battery will send the power and RLC will send the energy. These two energies will be boosted up. This is the DC link. In the DC link, voltage will be constant. By maintaining the voltage constant, converter is speed control will be used. This is the speed controller. This is the motor. In this project, permanent magnet DC motor will be used. Next, working of Working. DC voltage source. The heart of this system is the DC voltage source, typically a high capacity battery pack. This battery serves as the primary energy storage unit, providing power to the electric traction system. DC to DC boost converter. Connected to the battery is a DC to DC boost converter, which utilizes MOSFETs to increase the voltage level from the battery to the match the requirements of the electric traction system. This converter ensures efficient power transfer and voltage regulation. DC to DC buck converter. The DC to DC buck converter is controlled by pulse width modulation technique. This converter works in tandem with the boost converter to regulate the voltage supply to the electric motors. Electric permanent magnet motors positioned behind the electric vehicles are two electric permanent magnet motors. These motors are integral to the propulsion system, converting electrical energy from the battery into mechanical energy to drive the vehicle forward. The use of permanent magnets enhances efficiency and power density. Control technique use. The control strategy for the electric motors utilizes the Lipno technique. This technique provides a robust control framework for achieving stable and efficient operation of the motor. Next, coming to the simulation results. In this project, there will be four cases. Case one is we will keep the battery initial state of charge is 95% with 240 voltage. Then we will run the project. First, we will see the boost converter graphs. In these graphs, this is the voltage waveforms, this is the current waveforms. DC link voltage will be the boost up to the 340 voltage. This is the current waveform. Next, we will come to the buck converter waveforms. This is the buck converter voltage waveform and this is the boost converter. This is the buck converter current waveform. Next, we will come to the motor characteristics. By providing 240 voltage through boost buck converter operation, the speed will be the 1200 RPM and the voltage will be the 240 constant voltage because we are providing boost buck converter operation. This is the current waveforms. And next we will come to the second case. Change the capacity to the 75% with the voltage 240 voltage. Then see the waveforms of the boost converter. In this case, voltage drop will be decreases to the 60%, but voltage will be the constant to 40 voltage because we are providing controlling. We we attain maximum values in book, buck, boost, and motor characteristics. This is the voltage waveform and current waveform of boost converter. Next, buck converter. This is the voltage waveform and this is the current waveform. Same will be appear in the motor characteristics also. Same 240 voltage, speed will be 1200 RPM. In case 3, battery initial state of charge is 95% with 240 voltage and torque will be the 0%. Then we will see the waveforms of the then we will see the graphs of the boost buck and motor characteristics. Normally, in no load conditions, speed will be rapidly increased, but in ideal cases, speed will be infinity. In this case, we are providing controlling rated speed speed will be increased in permissible limit because of we are providing three we are providing boost buck converter controlling, so rated speed will be increased in permissible limit only. So we will see the waveforms of the boost buck motor characteristics. First we will see the boost converter. This is the waveforms of the boost converter. This is the voltage waveform and this is the current waveform. Speed will be DC link voltage will be increased to the 340 voltage, and we will see the buck converter modeling waveforms. This is the voltage waveform and this is the current waveform. Coming to the motor characteristics waveforms, this is the main. Speed will be increased to permissible limit. That means 1400 RPM. This is the waveforms of the motor characteristics. In case 4, without buck boost converter, we will see the waveforms of the boost buck. We will see the waveforms of the motor characteristics. By, by connecting the DC voltage source with 240 voltage. This is the waveforms of the voltage, current, and speed without buck boost converter operation. Without buck boost converter operation, there will be the no emissions reducing. So it's the by using buck boost converter operation, speed will be increased in 1200 RPM and emissions will be reduced by using buck boost converter. Next, coming to the advantage. Improved efficiency, emission reduction, enhanced performance, flexibility and adaptability, scalability, reliability and durability. Next, coming to the applications. Electric vehicles, hybrid electric vehicles, light electric vehicles, urban mobility solutions, and industrial and commercial applications. Finally, conclusion. I conclude by integrating a DC voltage source supplied by a battery, DC to DC boost and buck converters, and electric motors controlled by advanced techniques such as pulse width modulation and Lipno control. The scheme offers several advantages, including improved efficiency, emission reduction, enhanced performance, flexibility, scalability, reliability, and durability. Through comprehensive modeling, simulation, and experimental validation, we have demonstrated the feasibility and effectiveness of the proposed scheme. In achieving its objectives of optimizing energy efficiency, reducing emissions, and enhancing the overall performance of electric traction systems, in hybrid electric vehicles and electric vehicles. Our findings suggest that the use of advanced control techniques and modern power electronics components can significantly improve the efficiency and effectiveness of electric propulsion systems, paving the way for a more sustainable and environmental friendly future of transportation. Thank you.